Good afternoon, everybody. Last class, we have studied our specific materials which are required for the nuclear power production, and also got the highlights of the evolution of nuclear fuel cycle in India. I believe you must have got those information that this old our reactors, this Apsara and Cyrus is already decommissioned 2010, and now our new reactors, which are totally indigenous, Dhruva and new Apsara, they are taking care of full load of research reactors requirement. So with this, I start today's lecture, which is on the specific technologies which are required both for front end and back end of nuclear fuel cycle. And these technologies are also specifically required for maintaining your neutron economy. Means when you are getting these materials which are required for this reactor fuel and associated parts, we have to make them in such a way pure that there is no nuclear impurity, there is no neutron poison. So those requirements are very stringent requirements. For obtaining that, you need some specific procedures to be followed. So in this selective separation, first one is the elemental separation. Means there are some elements like boron, cadmium, gadolinium, many other, those who are not good for neutron economy, they have to be totally removed. Along with that, the first requirement is first you have to get the required material itself, like uranium. In the ore, it is only 0.05, 06, 07%. So you have to have some technologies with that. Selectively, you can get uranium. So when we go through that uranium mining and processing, we'll know some are physical methods, some are chemical methods. Same for thorium, zirconium also. And then comes that nuclear grade purity for removing all elemental impurities which are even in the trace quantities. So that is another requirement. Then for the back end, we have to do the fuel reprocessing. We have to decontaminate our waste. We have to manage our effluents. For those activities also, we need selective separation processes. And the method specifically used, first one is the leaching. You must be aware that from the ore, we do the leaching for getting uranium. And this is a solid liquid contact. Ore is solid. We have to have a leachant of liquid. And equipment used is pachukas or continuously start tank reactors. Or if it is not atmospheric pressure temperature, then we have to use the autoclaves. Similar way, after getting the solutions, we have to remove some impurities selectively. So we go for ion exchange. And this is not only for the ore, for many other nuclear material applications also. Ion exchange is required. This is also a solid liquid contact where we can have either packed column or we can go for pre-diced bed. The third important one is the solvent extraction. This is the most important one for all nuclear material. The solvent extraction is being used. Solvent extraction, many of you may be knowing, this is being atmospheric temperature pressure contact system, and quite efficient and economic. For most of our cycles, solvent extraction is being used. Now in the solvent extraction, back end and front end, both the ends we do, they are liquid contact systems. Are different contactors are there, like mixing settlers, slurry extractors, centrifugal contactors, or different type of column reactors. So about this we will learn little more, because these are very important equipment for the whole nuclear fuel cycle. We have membrane separations also. Membrane separations are used for water purification here, or for if it's decontamination of the nuclear backend, nuclear waste material. So this may be a liquid membranes like solvent dispersed in your membrane print, or solid supported membrane, solid supported liquid membranes, or we have composite membrane. Then we have many physical separations. As I was telling, this our ore is very lean. So when we get the rocks, you have to do gravity-based separations so that unnecessarily you don't have to take a whole lot of load in the leaching process. So physical separations based on their physical properties, either maybe gravity-based or magnetic. Then selective precipitation. Selective precipitation specifically for when we wanted to recover the uranium from a system, we do a very uranium selective precipitation process. Evaporation distillations, these are required mainly for back-end side for waste decontamination and processing. Absorptions we do for effluent management in many places. So for all this specific selective systems, we are having specific equipment now for refining, which I said when we have to do that minor amount of nuclear poisons removal. So that process we call at refining. For this refining and for processing of the back end waste spent fuels, we use either pulse columns, mixer settlers. These pulse columns are very good for remote handling, but it's having low efficiency when you increase the size of diameter of the column due to the back mixing. That way, mixer settlers are very effective equipment, but presence of solid, it creates problem. Now you must have seen at the title I have mentioned for non-critical systems, means systems which does not become nuclear critical. For them, sizing is not a very big issue. But what systems where nuclear criticality can be a problem, like plutonium or enriched uranium system, in those cases, sizing has to be taken care. We cannot go on just increasing sizing for capacity buildup. So there again, some other considerations will come. We will come to that part in the next slide. But here, when it is a non-critical system like your natural uranium or zirconium systems, there this considerations are taken care. So mixer settlers are not good for solid containing material. So in those cases, DAE has developed a slurry extractor, where it is a stage contactor. Pulse column is a differential contactor. Mixer settler is a stage contactor. Slurry extractor is in line with mixer settler. That is also a stage contactor. So efficiencies are good, and it can handle solid in the feed. Means slurry feed also up to certain extent it can handle. So this is the present choice for most of our in nuclear fuel complex also in BARC also. So here it comes. This is the top view of a mixer settler. You can see these are stages. So individual stages, as you know, this solvent extraction is a mass transfer based operation. So for first you have to do the mass transfer in this, and it is an equilibrium process. So once you do the mass transfer, these are the mixes. Here you have to mix the solvent and the feed material. The solvents are in most of the cases for our nuclear industry, tributyl phosphate is the ideal solvent, which is having a very selective uh, uh, solubility for this nuclear materials, and it is highly compatible with all of the other systems, and it is regenerated after use. So from the economic point of view also, it is very good, non-toxic. So from all points of view, TVP is a good one, and it is being used for all processes. Only thing for backend, some new solvents are also developed. That is due to some radiation stability problem and all. So those are few, but TVP is workhorse for the whole nuclear industry. Only thing, TVP cannot be used as a 100% TVP because of its density and viscosity. So generally we reduce it with hydrocarbon, maybe 30%, 40% TVP reduced with the hydrocarbons we use as a solvent. So this solvent along with the feed. Here feed material has to be in the nitrate system. Solvent TVP is suitable for nitrate medium. So feed material will be in the nitrate system. Feed and solvent will get mixed in the mixers. And from there, after mixing, mixers are needed only for this intimate contact so that you get good transfer area for mass transfer. And after that, as they are reached equilibrium, now unless you separate the phases and make them new contacts, mass transfer will not proceed. So you have to take out in the cyclers, you have to do a good phase separation. And the end, you have your flow dividers. So flow will be their countercurrent way. This is for the aqueous. Aqueous is going to the next mixer, and organic is overflowing to the previous mixer. So this countercurrent way they will proceed, and process will go on. As we said that mixer settlers are having good efficiencies near to your theoretical stages. So generally, you have to have maybe you can consider the stage efficiencies nearly 80%, and accordingly you can design your equipment. And this is your slurry extractor. I said this also is in line with mixer settlers. Similar stage contactors. This part is here mixer. So this mixer, the same way both the fluids are coming, like your solvent and the feed, and here mixing is by air. So compressed air is being used for mixing, and lifting air, organic and aqueous will be at the top and bottom, and they will move countercurrently as in case of mixer settlers. So you can see that here hold-up volume is very high. So where the solvent is costly or solvent gets degraded if it is in contact with the acid or radioactivity for a longer period, then these systems are not useful. So these will not be used for backend. This is used for the front end where criticality and radioactivity degradation is not an issue. This is the column. I said that column is also another equipment where you can do this solvent extraction process. So this is more used for the backend. Actually, initial days we started using columns, and even for the uranium processing also. But due to this inefficiency during the size increase due to back mixing, we stopped it, and then we went for mixer settler and slurry extractor. But in case of pulsed column, as size already is limited due to this criticality issue, means if you go on increasing the size, it can become nuclear critical. So there will be some specific sizes which you have to maintain. So in this case, efficiency loss is not a very big issue. Here you can see that this is the column, which is actual mass transfer zone. Inside that, you will be having cartridge of this stripped columns, stripped plates. So in that, by air pulsing, it will fluids will move and get mixed also during movements, and mass transfer will take place. There is no in between separation because we are not allowing throughout the column to attain equilibrium. Whereas in other cases where there's mixed stage equipment, we used to have reached equilibrium for each stage, and then we used to separate them for attaining the next equilibrium. But in these cases, here nowhere we are allowing them to come in equilibrium, so it can move ahead. One phase will go up, another phase is coming down, and at the end only we have the separators for the complete phase separation. When we are taking the products out, then after settling we are taking individual products. There is no cross flow. So this is more important for backend. Now there is one more contactor. This is the chart which we generally use for selection of the equipment. This centrifugal contactors. Centrifugal contactors are another type of contactors which actually was developed for sensitive processing of sensitive chemicals like your antibiotics and all, where residence time requirement should be much reduced inside the contactors. So the centrifugal extractors were developed there, and now this is used in backend where residence time is a problem. When it comes in from, there are some radioactivity point where when it comes in contact with the solvent, solvent gets degraded. So we have to reduce the residence time. For reducing that, we need some special aids. So centrifugal force is much higher than gravity force. So in the centrifugal conductors, centrifugal force is being used for mixing and also for settling. These centrifugal conductors can be staged conductors, or it can be a differential conductor like columns. So depending on your design, you can make it. Now only we will see that what are the basic points on which we select what type of units. So here you can see this when headroom is a constraint, once your building height is a constraint, then we cannot, then column is not a good choice. And mixer settlers and centrifugal conductors are useful. And when you need your floor area is small, then column is a better choice. When you need low hold up, then best is your centrifugal conductor, and next is PC. Mixer settler is not a mixer settler or the slurry extractor. They are similar way we treat. They are not a good choice. Reaching steady state quickly. In this case, this is average PC, and centrifugal conductors are the best one. Process flexibility, more or less all will be usable. Ability to tolerate solids. We have seen that mixer settler is not good for that. Even centrifugal extraction is also not good for that. Their columns are good. Another most important is that residence time. If long residence, sometimes you need a long residence time for good mixing or the reaching equilibrium. So in those cases, you can use your mixer settlers. So for all rare earth material, mixer settlers are the workhorse. Where we continuously use number of stages and mixer settlers. And shorter residence time, then you have to go for centrifugal conductors. For instrumentation and control, all are good. Ease of scale up is also more or less same. Capital cost, also not a very big concern for you. Throughput, this columns and centrifugal conductors both are good for this. But in case of mixer settlers, this has been given below average, that is for back end, not for the front end. Front end, you can go on increasing the sizes and throughput. So now, based on all this separative knowledges, we are just going to the zirconium technology to see how this zirconium is getting processed and where all the separation technologies are being used. Now, zirconium, as I said, zirconium is not directly a fuel element, but it is a fuel supportive tube. Inside the zirconium tubes, fuel pellets are kept, and this is must for this fuels to be inside reactor. So zirconium occurs in nature as zircon. Zircon sand is available in many places in India, and this is a silicate mineral which earlier used to earlier now also it is being used. More use was there in glass and ceramic industry. However, specific use of zirconium metal was highlighted only after development of nuclear industry. Why does nuclear industry like zirconium metal? The unique properties of zirconium and its alloys are low neutron absorption cross section. So once it is being inside, it does not absorb on neutrons, so neutron economy is maintained. And its phase transformation temperature is high, so relatively higher temperature it can see, no problem in that. And compatibility with fuel material, coolant, and associated moderator, all these materials. So considering all this, zirconium specific requirement is that it is low neutron absorption material. So zirconium has been selected for tube as a tube metal material for all PHWR reactors. Now, again, we call it as the reactor grade, because before taking it to the reactor, we have to purify it in such a way that there should not be any additional poisons for the neutrons or any other material. Even for mechanical strength and the other properties also has to be controlled. So based on that, its chemistry has to be maintained. So in this zircon sand, which contains along with zirconium always naturally hafnium. So this hafnium is a very big neutron poison. You know, hafnium is such a good neutron poison that it can be used as a reactor control material. So when it is going as a structural material, so hafnium has to be removed properly. And generally in the natural zirconium, we have around 2.5% hafnium. And reactor grade zirconium, the limit is around 25 ppm. Many other constants, this is the most important requirement. So the process goes like this. First, you have to remove the silica because it's a silicate material. So for this silica removal, there is a selective dissolution or water leaching after sodium hydroxide fusion. Once you give a sodium hydroxide fusion, that silica goes as soluble sodium silicate, and zirconium and hafnium remain as a insoluble cake. So this residual cake will be dissolved in nitric acid, because as I said that for tributyl phosphate to be used as solvent, you have to be in the nitric acid medium. So once it is taken dissolved in nitric acid, it has been prepared for particular feed concentration and acidity. Then we go for separation of hafnium. This hafnium can be separated by most efficient way by tributyl phosphate extraction. And for this hafnium separation, the equipment used is there a slurry extractor. The size is very big, and as they form quite stable emulsion during settling. So the big settlers are good for this, and very efficiently slurry extractors are being operated for several tons of zirconium processing. So after extraction, what happens in the extraction? Zirconium forms soluble complexes with tributyl phosphate, which goes to the from aqueous phase. Zirconium goes to the organic phase, and this organic is separated out for scrubbing. After scrubbing, you remove some partial impurities again, and then it will be stripped in the aqueous phase back. So earlier also it was zirconium nitrate before going through solvent extraction. Now also after stripping, whatever we get, that is also zirconium nitrate, but it is nuclear pure. What happens to all these impurities? Hafnium along with all impurities at the extraction stage goes along with the aqueous as raffinate. Zirconium has come as in the organic phase as extract, and hafnium and other impurities will go as raffinate in the aqueous phase, and it will be taken out. Now hafnium is also an important material for reactor control. It is needed, so that will be treated differently for control material preparation. And now this nuclear pure zirconium will be taken for zirconium metal production. So for this, the first step, once the purification is over, which is called the refining of zirconium is over, we precipitate zirconium hydroxide by using ammonium hydroxide. And after this, we do a calcination to get zirconium oxide, and then this zirconium oxide will be converted to zirconium chloride. But as zirconium oxide is very stable compound, so it needs a carbothermic chlorination. Means it has to be mixed with carbon and then heating at around 900 degrees centigrade, and then we pass chlorine. So then only it will become zirconium chloride, and carbon will get oxidized and go away as a emission effluent. So this zirconium chloride is actually at room temperature it is solid and it directly vaporizes when it is heated at around 300 or so. So when we produce, it will be a vapor, but we take out that zirconium chloride vapor to a colder place and make it solid. Now this solid zirconium chloride has to be reduced by magnesium to have zirconium metal. What a long process you can see. And this magnesiothermic reduction or the metallothermic reduction, this is also like solvent extraction is a very common process for most of the nuclear material. This metallothermic reduction is also very common for all other, even for uranium, thorium, plutonium, everywhere we will do this metallothermic reactions. Here it is magnesium, some places it may be calcium. So magnesiothermic reduction of zirconium chloride is a very complex process. This zirconium chloride will be in the solid, in the long reactors are there, which will be heated at around 1900 to 1000 degree, 900 around. Chlorination was in 1000, I think. Yeah, chlorination is in 1000 and this is around 900. So this reactor top zirconium chloride will be there and bottom will have magnesium blocks. Once it is heated, magnesium will become liquid and zirconium will become vapor. So zirconium vapor will come down to react with magnesium and there solid zirconium will be formed, which will get precipitated there. And this process continues until zirconium chloride is available. And this reaction is pressure and temperature dependent. The pressure is maintained through safety valves and all. And by checking the pressure, we come to know that endpoints the reaction. After the reaction is over, it is pulled down. Now, if you take out the material inside this magnesium and our magnesium and along with your product materials, this will be again contaminated with some amount of magnesium chloride and magnesium. So that needs again vacuum distillation. The zirconium which has been formed, that needs vacuum distillation. After vacuum distillation, you remove all remaining magnesium and magnesium chloride and you get zirconium sponge. So still it is not complete for your production of the component. This magnesium sponge has to be made as ingots. And generally, what do they do? As zirconium is always used as a alloy material, so they first cut down the zirconium sponge in a smaller size, then mix with alloying element, press it with the briquettes, weld them to make a electrode, and then it is again melted. And quite a few number of meltings are needed to get a homogenized product. And after that, you get a homogenized billet of zirconium alloy, zircaloy 2, 4, or zirconium, depending on the alloying element mixed with that. And now it is ready for fabrication of your zirconium components. For us, we need the fuel tube that is nearly half an inch, around 13 millimeter with 0.3 mm wall thickness tubes, which is done by extrusion. And pilgering is required for this bigger calandria fabrication. So such a long process, and where how many times you have seen that selective separation processes are used. If we see the material of construction in this whole process, you will be surprised because chloride is very corrosive. So for that, chloride cans has to be employed. And then other materials which are heat sensitivity is required. So there stainless steel different grades will be required. And for many other materials like your sponge storage and all, you have to be very careful because zirconium dust or the particles are highly pyrophoric. It catches fire. So considering all these problems, it's a very big challenge. And in the whole world, very few countries are having this technologies or mastered these technologies. India is really a master in that, and they produce large quantities of zirconium alloys. Just for your idea, for a 540 megawatt reactor, maybe yearly we need 37 to 40 tons, and the first charge maybe 55 tons. So this is the way they have to go on producing for so many 18, if 18 reactors are operating kg of this, they have to give so many reactors feed materials with this. So that is their production requirement. With that, I think now we will be moving to the isotopic separation. First part was your part, separation of elements, elemental separation, where we have seen it is a chemical process, and different systems have been followed for separation of that. Now, in case of isotopic separations are needed for what? Isotopic separations are needed also for this neutron balancing, because if you see that if the reactor is using heavy water and natural uranium, so in that heavy water you have to do a isotopic enrichment. What is heavy water? There deuterium is much higher percentage. In the normal water, light water, if we have 150 ppm, heavy water, which is needed as a moderator for them, will be having above than 99% D2. So such high isotopic enrichment is needed for heavy water. And in other case where you are using light water, you have to have enriched uranium. So in this enriched uranium also, you have to have the isotopic separation. So in this isotopic separation, as we see that isotopes of an element have very similar chemical and gross physical properties. That makes their separation particularly difficult and necessitates the development of concepts and processes specially adapted for the purpose. That means for this isotopic separation, different processes specifically for this separation, they have been developed. So process selection criteria, if we see that isotopic separation processes, they may be based on the driving force, they may be classified into 4 classes. The first one is the chemical process based, where your separation factor is proportional to delta m by m square, where delta m is the difference of the molecular weight between two isotopes, and m is average molecular weight. So delta m by m square, this figure becomes very low if m is high, means it is a heavy material. So in those cases, this free energy difference based chemical processes are not suitable. Though it is energy efficient, but due to these very low separation factors, they will not be suitable. So distillation chemical exchange, these are the chemical processes where light isotopes are being separated by that. And for heavy elements, we have kinetic based separation processes, where separation factor is proportional to delta m by m, and these are gases, gas diffusions, gas centrifuges. These processes are under that category. So other categories are, these are the 2 categories. Then third category is where we are at gas centrifuge is in the third category, where along with that physical separation, we are adding additional one outside force like centrifugal force. So gas centrifuge is the third category, where along with this kinetics, we are adding, it is being added by additional force, which will increase this separation. And the fourth one is laser isotope separation, where we are specifically one particular isotope will be excited by laser and that will be taken up. So based on all these processes, now we can see the distillation chemical exchange cannot be used for the heavy elements, though they are energy efficient, and other processes can be used for heavy elements. It depends again on the enrichment ratio also. If the enrichment ratio is very high, like heavy water, where we have to go for a very high enrichment ratios beyond 7,000 or more than that separation factors. So in these cases, we have to go for chemical processes, either chemical exchange or distillation, because they are self-fractionating type equilibrium-based processes. Countercurrent movement, we can make contacting equipments in such a way that continuous operation is feasible, and we can go on adding the capacity. And if the scale of production is very low, but you need a very high separation for a small quantity, then we can go for target-oriented things like laser isotope and all. So this you all know. I'm not putting part in that. There's application of this one is moderator, and deuterium tritiums are considered to be the best fuel for fusion reactors, used as tracer in chemistry and hydrology. You have seen your earlier classes. And natural abundance is only 130 to 150 ppm in all hydrogen containing compounds. Now, here this, as we said, that separation of hydrogen isotopes, including your even D2O also, as separation factor is small and your enrichment requirement is very high, so generally number of stages requirement will be very high. So this will be total column volume in terms of diameter and column height is quite big. Energy requirements also there, but considerably this heavy water board is decreasing the specific energy requirement for this by utilizing all waste heat. So at those points, when you go through properly, you will know that so many special cares have been taken to make the processes energy efficient. And if you see this, this are only the mass transfer rate and separation factor. This is guided by pressure and temperature of the system. So again, pressure and temperature will guide your total power volume and energy requirements. So by balancing all this, we have to come to a particular number of transfer units, and then some optimized recovery we have to consider, and then you have to design your equipment. General challenges, the overall enrichment ratio, as I said, 7,000 or more. Low abundance implies large plant volumes. So initially, you have to have very big volume of towers, and low separation factors means you have to have number of equilibrium stages more. But these are being equilibrium processes, which is much more energy efficient compared to other physical based processes. So these are few examples. And this water H2S process, what we call. So when they come in contact, whatever deuterium is there in that H2S, that gets transferred to water, and water gets richer in D. So it goes on increasing its D2O content. Similar, you can see that this is the plant quota based on this technology, water H2S exchange process. So the stall columns, mostly they will be outside open atmosphere, so that you can have these big columns there. Advantage of this process, though, limitation of the feed. It's written in this means water is available and H2 is also available, but H2 is you have to take it in some supplies where the H2S gases are generated as a source. And H2S being very toxic and corrosive, you have to take care of all conditions. So safety is a very big concern here. And exchange rate is higher compared to other processes. A moderate pressure is react optimum plant volume. Disadvantages, as I said, it's very toxic and corrosive, so material of construction and industrial safety has to be taken care properly. Recovery is not that high. High energy consumption. High energy consumption will be there for most of the isotopic separation processes. This other process is ammonia hydrogen exchange process. Here, this ammonia, when it is coming in contact with HD, passing through this countercurrent column, then D of hydrogen is getting transferred to the ammonia, and this hydrogen is getting linear in deuterium. So here also, if you get your feed availability is good, high separation factor, compact plant size, high recovery. Recovery is quite good here. But limited feed availability, it is meant that it has to be in association with some fertilizer industry or so where the feed will be available. Otherwise, everywhere getting this low cost ammonia will not be possible. So that is the point, that limited feed availability. Hence, it has to be co-located in the fertilizer plant. Then ammonia is also toxic and corrosive. It's having slightly slower kinetics. So potassium amide is used as a catalyst for the system. High efficiency conducting equipment is required. So contactors having this specific intermediate processes in that. And pressure, high pressure option, it is around 250 atmospheric. So we have to design the columns in that way. So these are few processes for your hydrogen isotope or D2O separations. It is simple distillation one. And for heavier, we could see that thermal diffusion is a simple process that does not need complex and expensive equipment. Large separation factors can be possible depending upon the shape and size of the column. However, it is suitable only for small scale operations. So in this case, you can see we have created a column where one side is cold well, another side is hot well, and considering the relative diffusion transport of isotopic species against the concentration gradient created by this temperature difference. So depleted UF6, you can see the feed is coming in between of the column, and this your column current has been created, providing your thermal gradient, and at the top we are taking uranium, enriched uranium, and the bottom we are taking depleted. Now, as you may be aware that for the uranium, for any isotopic separations, you need feed either in the liquid form or gaseous form. So for water anyway, it is liquid, so there is no problem. But for uranium, liquid you cannot consider. So only one compound of uranium, UF6, which is gaseous, though normal vapor pressure at room temperature is not very high, but with increasing the temperature, it can get fully vaporized. So this is also directly from solid directly goes to vapor. So UF6 has been considered the only compound of uranium for taking an isotopic separation operation. So here fluorine does not have any other isotope. So that way it becomes much simpler. Uranium isotope only can be considered. So this thermal diffusion is one process which initially people used to use in a large scale. But gas diffusion accounts for the 40% of worldwide uranium-235 enrichment capacity. It's well proven and reliable technology. Process mechanism is molecular diffusion. As you know, this here we have our specific membrane of particular specification, and we are putting UF6 gas here with high pressure, and inside this it's coming as a medium pressure. And as you know, this when the full thing is in thermal equilibrium, your kinetic energy for whole system will be same, but that lower molecular weight species will be having higher speed. So they will be moving more faster, and their probability of reaching towards this membrane site is more. And once you make design it such a way that backflow resistant membranes, it will be separated and it will be staying there. So that way, this upper portion will be enriched. So this is the method used here for this enrichment. And for other methods, which we call that centrifugation, where I said that along with the kinetic movements, we are improving the separation by adding additional one more force, that is the centrifugal force. So here you can see inside this separation unit we call, that will be a column sort of thing. We are putting UF6 centrally on this particular level, and this whole cylinder is rotated at a very high speed. And as you know, that centrifugal force for this higher pitch isotope will be more, it will go towards periphery, and lighter isotopes will get towards center. And there additionally there is a thermal driving force is also created. So in combination of that, we have made a circuit where we can take that depleted things are coming here, and enriched one is coming to this center tube. So the very, very difficult pressure balance is needed there. First of all, it has to be totally evacuated at the initial level, and then only you can put your UF6. And this is called one separation unit. And if you see a stage, the separation units are having very small capacities. Our total hold up will be very small. So maybe 1,000 separation units will form one stage of the separation process. And as the separation factor is not high, so here also you need very large number of stages. So this separation units connected parallelly with the same feed forms the stage, and number of stages connected serially from the cascade of your enrichment process. I think with that, I end today's lecture. If there is any question, I'll be happy to answer.